Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Okay, hi, Ligang, can you share your screen?
Yes.
Okay.
So you
hi,
can see my screen, right? Okay.
Okay, thank you. Hi, everyone. Welcome to the Computational Fabrication Seminar. Today, we have 2 speakers, Ligang Liu and Lu Lin, to share their research on lightweight and porous structure modeling. We will have a short Q&A section at the end of the talks. If you have any question, please post it in the YouTube live chat box on the right of the screen. Our motivational talk is given by Professor Ligang Liu. Ligang Liu is a professor at the University of Science and Technology of China. He received his PhD from Zhejiang University in 2001. His research interests include computer graphics and geometry processing. He served as the conference co-chair or program co-chairs for many conferences. He currently serves as the steering committee member of GMP, the secretary of Asia Graphics Association, and the associated editors for journals including IEEE TVCG and CAGD, and so on. So now the stage is yours, Professor Ligang.
Okay. Thanks, Peng, for the nice invitation, and I'm very glad to give my talk in this special forum. It's really nice that we have a forum like this one on computational fabrication. So as you know, computational fabrication has increased attention from all kinds of. Sorry. So let me turn my screen on. Okay. Okay. Yeah. So my talk today is about the lightweight structure modeling and optimization. So let's take a look at this picture. So the famous architecture Louis Souverain coined this phrase: "Form follows function." So this is an architecture phrase. So it means that it refers to the idea that an object or a building's exterior design should reflect the different interior functions, so such as the buildings shown here. So any structure designed intelligently and responsibly aspires to be as light as possible. So the form means the design of the object, and the follows means that the form comes before function, and the function means the use of the object. So as we understand, every single object has its form as well as its function. Form generally means the shape, the structure, and the topology of the object. And the function means the strength, stiffness, and the mechanism of the object. So it's for proper use in the general life. So from the ecological point of view, so the lightweight structures are material efficient because the material strengths are optimized used. That means that no resources are wasted. So people want to minimize the usage of the material in our object, so such that the object can be cost efficiently fabricated. So as we can see in this picture, we have all kinds of different lightweight structures in our daily lives. For example, the architecture and the biology structures. So let's take an example of the light structure here. So here is the aircraft wings. So you can see there are lots of lightweight structures inside the aircraft wings. We have different kinds of ribs or skins and stringers inside the aircraft wings, so that the wings can be very light during its flight. Okay, so here is an example on the structure and topology optimization. So given a chair that people sit on it, so we can reduce or decrease the material used in this chair. And you can see that with some technology, we can optimize the structure and the topology of the chair, and as you can see here. So here is the animation which shows how the redundant materials are removed from some object like this one. And you can see that with optimization goes on, and more wasted material can be removed, so that we can get the final result as shown here. And these objects can be very strengthened and stiff as well, because the optimization can satisfy the different kinds of constraints with external forces, like something like that. And here is another example showing how the optimization removes the redundant material in an object, and the color shows the stress forces or something like this. Okay, and people develop different kinds of technology on the lightweight structure optimization. Generally speaking, there are three kinds of optimization goals. That is the size optimization, shape optimization, and the topology optimization. So as shown in this figure, the left is the input and the right is the output. And you can see that the size optimization aims to optimize the sizes or the length or the width of some structures. And the shape optimization wants to change the shape of the interior voids. And the topology optimization tries to minimize some the topology structure inside the object. So here is the general mathematical formulation on the lightweight optimization. So as shown in this left figure, so let me explain some notations here. So here, let me show the point. Okay, here is the dielectric boundary. So that means that the boundary here is fixed. And here is used external roads, so people can conduct some external forces over here. And all the other boundaries are free boundaries, so you can move the boundary or minimize the displacement of this boundary. And with some constraints, for example, here we have some fixed material, and we don't allow some material shown here. So and then the other region is the free material region. So generally, we have the constitutive models for this for some kind of special of the material, and we have the formulation like this. So generally, we have the cost function called complements or strength cost function, and we have lots of different kinds of constraints as shown here. So the first one is the stiffness equation. That means the object should be in the equivalent state when the forces are applied. And here, rho I is the design variables. That means each point or each voxel can be 1 or 0. And here, the last one, generally we have some volume constraints. For example, we don't allow the volumes of the objects to be larger than some threshold. Okay, so this is an iterative optimization process for the lightweight structure of optimization. So given initial design domain, and we divided the domain into different kinds of finite elements. We call it tessellation, and then we get from the initialization, we can iteratively optimize the structures one by one, and finally we get the results. So different kinds of optimization methods have different kinds of process, but finally we have a very reasonable or feasible optimized structure like here. And in sometimes we can mix different kinds of materials for lightweight structure. In some special cases, for example, here we show two materials for this example. So you can see with different mixture of the two material, we can have different structures inside, and also the objects can have different mechanism of properties. Okay, in our real world, so we have lots of types of materials from elastic, plastic, and also some cellular materials, relative structures, etc. So here you can see that the Young's modulus of different materials are from very large to very minor to very large. So in our world, we have to handle different kinds of materials in the optimization, and each type of material has different mechanical property, and we have to exploit these properties to achieve optimal results in our optimization. So there are lots of challenges in this optimization. So as you know, we use a very large number of finite elements. So we call the pixels or voxels in 3D or 2D. And then we have a binary decision for each voxel. So that means that if we have a large number of elements, we have a huge space for searching the design results. So people tries to develop different kinds of technology to try to solve this complicated optimization. For example, we want to convert the discrete optimization to some continuous design so that we can use some high-level optimization methods like the derivatives. And also we want to define some parametric structures with very small number of design variables so that we can reduce the scale of this optimization, or we can find some object functions that with cheap derivatives, such as something like that. Okay, so let me show some different types of lightweight structures here. So from my point of view, there are different scale of lightweight structures like microstructure, or some mixture structure. And in some paper, we can also define some mesostructure, something like that. Okay, so this suspends some particular parametric structures. So people can use charts, frames, or Voronoi diagrams, or some rip-shear the structure for lightweight structure design. And in these structures, we have different kinds of parameters. For example, for this figure, so the authors use the frames. So each frame has its length and the radius and the connectivity between the nodes. So we have a small number of parameters to be optimized. And this is another structure, and we call it microstructures. So people can define different elements of the microstructure so that we can compose all the microstructures to for creating larger objects. And we can define different microstructures in the cells, and then we have different kinds of mechanical properties in these objects. And people also use some mathematical functions like the Tpms. I believe that Linda will introduce the details of their work on this direction. And also we can synthesize some complicated structures from a given sample. This was coined of as texture synthesis from 2D to 3D. And we have many other cellular lattice structure. So you can see that in material science, they have a journal called Cellular Materials. So, and actually in material science, they have defined, or they have developed many kinds of cellular lattice in their community. And also you can see here, we have lots of solid forms. And also we have some composite structures. Composite structure means that the structure of the material is made of two or more constitutive materials. So they can mix the different kinds of structures into more complicated structure. And this another complicated or complex material, we call it functionally graded material. And you can see here the density of the material can change gradually from dense to sparse, something like that. Okay, you can create different kinds of objects with the special mechanism. And in our nature, we have many biological structures, and then you can see that most of the structures are lightweight. And then you can see here we have this spider silk, the bird, and the eyes. And people use many other special structures with, for example, with negative Poisson ratio, and you can see how the structure was composed to generate such kind of special structure. Okay, so for different kinds of lightweight structures, we have different kinds of optimization methods. So as far as I know, there are many different optimization methods. So some famous one shown here, I just a few of them. Includes the simple homogenization, ESO-based or level set, such as that. Okay, so Linda will introduce more details about these works later. So in our group, we have also done some works on lightweight modeling and optimization. So I will get a very quick introduction on these works. So this is my first work on this direction. So this work was published 7 or 8 years ago. We inspired from the frame structure used in the architecture. So apply the structure optimization for 3D printing. So you can see here the variable, the design variable includes the length, the radius, and also the node positions of the frames, so that we can minimize the structure to reduce the materials used in the 3D printing. And there's another work on design the reinforced shear structures. So this kind of structure is also widely used in architecture and the boat design. So with the sparse structure of the grip and shear structures, we can minimize the material used in these objects as well. And this is our recent work on Tpms, and Linda will introduce their work on this topic as well. And in this work, we, as far as I know, we have developed the first mathematical optimization for this structure. So Tpms has very good properties like smoothness, continuity, and connectivity, and controllable. And this kind of structure has been widely used in many areas, including engineering, medical sciences, and civil engineering. And here are some examples generated by our methods. You can see that this kind of structure is very, very nice, that can be fabricated with different 3D printers like SLA, SLS, and FDM as well. And this is also our very recent work on 4D printing. So 4D printing is very simple. It's a 3D printing with some smart material. So the smart material is a kind of stimulate responsive human memory materials that can be deformed from their permanent shape to a temporary shape when heated with external forces applied. And here is the example that generated by our methods. And you can see that due to the shape memory effect, the object will keep at the temporary shape when the environment temperature is decreased and the external forces are removed. Then the shape can turn back to the permanent shape after being reheated. So with this kind of property, we can optimize the mixture of the shape memory material and the elastic material to satisfy the user constraint. And we have also developed some applications to invalidate this architecture, and you can see that. So let me skip the first application, and let us take a look at this second application. So the grab cannot grab the ping pong ball as it's a permanent shape. Then we can hit it and deform the shape of the grab, and so that the grab can grab can get the ball when it hit it. Okay, so time's up, and so let me make a very short summary on my talk. So as shown in my talk, that we have lots of different kinds of structures, like language structures. But so there are still lots of challenges on this direction. As you can see that for these structures shown in the bone, so we don't have efficient mathematical representation for this kind of very complicated language structures. So this is the first challenge. And also the general FEM-based analysis is not able to analyze this the large scale of the system. And the optimization is also another bottleneck for generate such kind of complicated language structures. Okay, so that is, and I want to acknowledge all my colleagues and collaborators, and also the online resources in the website, which are used in my talk. Okay, so this is the end of my talk, and thank you very much.
Okay, thanks, Ligang, for the inspiring talk. So our deep dive talk will be given by Ligang Liu.
Okay, so thank you very much for Professor Song for the introduction, and I'm very glad, and it's my really pleasure to be here to present our work for this computational fabrication seminar. And I want to show my appreciation to the organizing committee, because I have joined the last talks and really enjoyed it. Okay, so today my topic is porous structure modeling. It follows Ligang's slides, and in this talk I will mainly talk about the porous structure. So porous structure or porous material. What is a porous material? Actually, the conception is very simple. Porous material is just a material contains pores. But porous material has very highly developed internal surface that conveys specific functionalities. For example, we can see these porous materials in the nature. For example, the soap bubble, the rock, the coral, and the bones, bread, sponge, etc. So thanks to the very nice physical functionalities caused by these highly developed pores, it has been widely utilized in industry for many years, actually. For example, you can see the corrugated board as heat exchanger, the sneaker insole, etc. So actually, the physical properties includes like the lightweight but strong, like the energy absorbing, like the large range of elasticity and high heat exchanging efficiency and so on. And it's also applied for various materials like paper, metal, plastics, and ceramics, metal, etc. So let's look at the features of porous structures. Depending on whether the cells are isolated from each other or they are connected with each other, they can be divided into closed cell porous structures or open cell porous structures. Depending on the direction of the pores, we can group them into isotropic porous structures or anisotropic porous structures. So since we know that there are so many beautiful physical properties for these porous structures, and our problem is how to model these porous structures such that they can convey these physical properties. So let's look at the porous structures modeling. If we considering the modeling objectives from the aspect of functionality, we want controllable anisotropy, we want controllable porosity, and of course we want very target mechanical properties as we have seen in the last pages. But we also need to satisfy the printability constraints. For example, the solid parts need to be connected, and if the pores are connected as well, and they will be very friendly for many powder-based 3D printing techniques. So I would like to briefly review the porous modeling methodologies. First is top-down approach. So it's like we give a 3D shape and we generate this 3D. Examine these 3D porous structures inside the given shape, but we're following a top-down manner. That is, we build a constitutive equation and we solve both the physical properties and geometric structures simultaneously until we have this kind of structures. Another group of the methodology is bottom-up approach. That is, we can see most microstructures. We start from predefined optimized microstructure in a regular form. For example, this alt-chat here, and we fill this the given space with this kind of microstructure. So this is another group, and actually this group of approaches is developing very fast. So in recent years, researchers also combine the pros of the two different kinds of the approaches. That is a two-scale approach, and which benefits either side to build the both high resolution structures and with very reasonable computational cost. Okay, so from another criteria, if we're considering how the structure is represented and how the optimization is performed, I also group the current methods into three groups: the topology optimization method, the implicit function-driven method, and parametric kernel-driven method. So next, I will briefly introduce the literature following this kind of category. Okay, so first we can see the topology optimization, which is a dominant method for years because it builds the constitutive equation and the fabrication constraints and other physical constraints together into an integrated equation such that we can directly solve it. The left part is the bottom-up approach, and the right part is top-down approach. So we can see that now researchers have put effort to combine different constraints like the local volume ratio, like the directional of this part structure in the topology optimization methods. And as well, topology optimization method can be also applied in the microstructure level, such that they can have better, they can have optimized physical properties as long as they have the very strict boundary conditions. So another group is implicit function driven. Still, the left part is bottom up, and the right part I label them as the top down. So sorry, as the bottom up. Please switch it. So so this work is just mentioned by Ligang. This is the very latest work with Tpms, and in their work they optimize the both the structure and both the size and the topologies of the Tpms to achieve the high stiffness. So later I will also elaborate on the Tpms method. So another is parametric kernel-driven methods. So this is the goal of the parametric kernel-driven methods is to use the parametric form to represent the huge variables of the voxels or other finite elements in topology optimization, such that the variables in the optimization is a limited number, and the optimization can be performed kind of fast and rapidly. For example, Ligang has shown the work with the frame scheme work, very impressive one, and more and more microstructure design works on this on the right part. So they are basically made the strut in a parametric form, and then they can optimize the strut with a limited number of parameters such that we can achieve the target shape. Werner diagram is also a very frequently used option to build the internal structures in the shape. For example, this is our work in 2014. We use Werner diagram, and Matthias et al. They have a series of great works on the Werner forms. They use either the Werner, the strut of the Werner form, or the walls of the Werner form. So use this kind of Werner forms, and this is a stochastic structure, and it's a very typical top-down approach. Okay, so talking about the parametric kernels, there are many options. For example, we can use the spheres. We can also use the metro truss as the parametric element. And if we're considering the self-support property, we can also use the rhombic structures. Okay, there are increasing number of such different researches on different parametric kernels to optimize internal structures. As I just said, both methods, either top-down or bottom-up, they have their own pros and cons. So the two-scale approach is actually combining the pros of either of each approach. So we can optimize the material distribution in the cost level, and then we can fill the microstructure to obtain the very specific physical properties and with high resolution. Okay, so this is the short, brief review of the current work, and from now on, I will introduce some details. Our first work is the honeycomb one. This is a typical parametric kernel-driven one. Today I will talk about the Tpms method and the kernel-based method to produce the organic porous shape. Okay, so let's first look into this project. So Tpms is really very appropriate for the microstructure design or either the integral structure design. So it has a very simple form, and it is of smoothness and double connectivity. So we can see there are variations of the different Tpms forms. Okay, so we take the most simple one called P surface. That is the primitive Tpms as example. So it's actually an implicit function. So for this function it's triply periodical. That is, it can grow infinitely to the 3 orthogonal directions. So for this P surface, we can embed the periodicity function, that is Px in the function, and such that we can control the periodicity of this Tpms form. For example, this is the constant one, and this we just increasing the periodicity along the bar, such that we can get from denser to sparser Tpms distribution. We can also represent this periodicity function as using a pre-computed scalar field, such that it follows the material distribution in advance, and we can get a good initialization. So we can see from this Keaton model, Tpms is connected, but when it is filled in a given shape, it needs to be clipped to fit in a given shape. So the cliption actually causes troubles for these structures. For example, here we can see that it might be turned into multiple components after clipping. So we need to figure out a method to make it local connected, such that we have the one component. So this is a printability constraint, that is the solid part need to be connected. So we can use very simple operators. That is, we apply a Gaussian function on the periodicity function, such that we can locally increase or decrease the periodicity. Usually decrease the periodicity such that they are denser and they can get connected. So this is the detail, and we use this Gaussian kernel to tune this periodicity function. Okay, so after tuning this periodicity, we can get a connected component of this Tpms part. Okay, so considering the computation, the fabrication constraints, the self-supporting is another constraint. That is for most fabrication fabrication techniques, we want the project to we want the object to be self-supporting. So self-support is a very well-known criteria that is defined by the subtended angle and the tolerance area. So we can see that for this Tpms structure, the red parts are not self-supporting. So we need to optimize it locally such that they are getting self-supported. So this is also very simple, and we can just add a parameter function gamma x along the printing direction. That is the z direction here, and we can increase or this z direction's amplitude, and such that it can be locally tuned and fulfill this self-supportness constraint. Okay, once we have these small bricks of the Tpms, so we get connected one, we get self-supported one, and we can consider another thing, how to utilize the very nice properties of Tpms. Because Tpms is really smooth, so why not build a channel of Tpms? That is, we can simply compute the offset of the Tpms, and we get a channel that is smooth everywhere, and it can guide the fluid go through the channel. So it's very simple to compute because here we use the implicit function. We only need to change the value of the level set, and also need to be careful to on the offset such that there's no self-intersection. So once we have this channel, and it will be very interesting to consider how to use this channel. So we choose to inject another material in the channel such that we can combine the 3D printing and injection together. So here is really interesting part. So I want to say a bit more words on it. That is, 3D printing is very good at printing complex geometry, but it encounters problem of low speed, a limited number of limited choices of materials, and relatively high cost. But casting or molding is have the very opposite cons and pros. That is high speed, and it has variation, a large variation of materials, and the cost is relatively low. So why not combine the pros of both two fabrication techniques together to propose the hybrid fabrication? So this is our idea. So this is a binding model, and we are injecting the epoxy resin in the binding model in the pre-computed Tpms channel. So it's very fast, and the epoxy resin solidifies in the normal temperature after 5 minutes. So it's super fast, and we get the solid one. Okay, so this is the idea, and since the Tpms channel is one component, and it's self-supported, and it can be easily fabricated in advance, and then we inject the second material. Okay, so we formulate the problem into the Tpms channel optimization problem. That is, we want to optimize the Tpms channel's structure, and such that we can achieve the high strength to volume ratio. That's shown here. So the two variables are the periodicity px and the width. Actually, the width is the local parameter everywhere. that we can control the local width of this channel. Okay, but let's see the functional space. Here the sample A and B, the periodicity are the same for A and B, and also for C, they have it has the lower periodicity, and the D sample has very dense periodicity. We can see that the correlation is not very clear, and it's not monotonic, and the whole designing the optimizing space is nonlinear. So we need to very carefully design the optimization strategy. Okay, actually we employ the interleaving method. We optimize the width and the periodicity interleavingly. So for the width, it's a local tuning. So here we only need to be very careful to avoid self-intersections, and we omit the details. And for the periodicity optimization, it's kind of interesting that we, for example, here for strong regions like this regions in the box. So we want to increase periodicity such that the material used is lower. That is, we reduce the channel capacity because we do not need this much material to be injected. So for weak regions, we also want to increase periodicity because here we want more injected material to fill in. So this is very tricky part. So here is the optimization process. Usually we need one or two or three rounds for adjusting the Tpms frequencies. That is called the periodicity optimization, this P optimization. And we use a little bit more iterations for local tuning the widths of the Tpms channels, such that they are tuning in a fine scale. Okay, that's almost end to the whole story, but we need to be also careful to considering the injection. The injection part, we need to compute the local maximal. That is, if we make the whole object closed, there would be some air pocket that air cannot be escaped easily because we only inject from one hole. So usually for the this is a well-digged problem in the molding researches. So here we just employ their methods to our escaping hole computation. For example, here we can consider the shaking of alpha angle, and after shaking, the very local shaking, these 2 points can be closed, and there would not be air pockets. That is, we only need to open small holes here and here. So for this dragon model, we really choose the non-salient part to dig the hole to inject the material. So here's a red angle shows where we inject the material, and the two green arrows show the air escaping holes. Okay, so another interesting part is the injected material. As I said, there are a really large option of the injected materials. In the video we showed just now, we use the epoxy resin to fill in, which are very frequently used for the DIY makers home. But we can also add the carbon fiber in the epoxy resin, such that we have enhanced strength. For example, if we use the PLA, that is a 3D printing material, and the yield strength is only 49 megapar, and the epoxy resin is kind of a higher yielding strength. But if we consider the 10% carbon fiber in the resin, we can get two times higher strength of the new material. So, but these experiments need to be very careful. We have a collaborator from the material science, so it needs to be very careful, very protective. Okay, so if we consider the two different materials here, the PLA, this is Young's modulus, and for the carbon fiber resin, and it's double of that of PLA. So they have the same Poisson ratio, and after this is just a simulation, and we can show that our results can sustain very high external forces. Okay, so there are more results, and we can the models are on our project page. Okay, so this is the middle work I just introduced. I didn't talk about much details on the optimization of the structures, and for the latest research progress, I really recommend the Ligang's work just published. They have a better optimization formulation on the Tpms structure. Okay, so I will talk about the next one. That is this one. We can see that it's very it is very different looking with the first two kittens. It's kind of more stochastic, more organic, right? That's our target. So let's look at the real porous structure. So this is form, just natural form. So our question is, most of the works are taking the solid part as the optimization element to present parametric forms of the solid part, or to use implicit functions to represent the solid part. But why not represent the pore? Why not represent the pore? Then we can represent the pore shape and the pores distribution, and we can really do the biomimetic thing. Okay, if we can, then how to represent each pore's isotropy is the question. Another question is how to achieve double connectivity, how to guarantee the double connectivity as we show in the Tpms work. Okay, so for the first question, we propose a tensor-based Gaussian kernel to represent the pore instead of the solid. And for the second part, we really need to have the guarantee. So we employ the Morse-Melt complex to enforce the double connectivity. So as shown here, we first model the green part, which are pores, and then we actually simultaneously we get the blue one, which has a porous structure. So that's the idea, and also the motivation of this work. So if we want to represent the pore, and also with directions, 3D tensor is good choice for representing the pore shape. So it's like this figure, and a tensor. A 3D tensor is like we have the 3 orthogonal principal directions, and then if we apply to a sphere, and we get an ellipsoidal shape. Then we propose the tensor-based Gaussian kernel. That is, we use the TI, which is the tensor matrix in the distance matrix, and such that we can get a directional Gaussian kernel. This is not new, but it hasn't been used to model the pores. Okay, so let's take a 2D illustration for the illustration. Here we have 3 Gaussian kernels in the 3 Gaussian 2D Gaussian kernels. So if we consider the Gaussian the ISO values of the Gaussian kernels, the 3 kernels, we remember we use the kernel to represent the pore. So the higher value the pore shape it would be, and so the inner shape is the pore, and the lower value is solid part of the model. So the problem is how to find an optimized level set value, all the distributions of the kernels, all the tensors of the kernels, and more parameters. So so the whole problem is like this: we have a model, and we have a tensor field, and we have the requirements such as the porosity, the number of kernels, the size of kernels, the shape of kernels, etc. And we have the porous model as the green one, and then we simultaneously get the porous model, which is the this one. So this is the idea. Actually, it's very simple if we considering this tensor-based Gaussian kernel, because we only need to consider the tensor matrix. So I will emphasize how to guarantee the connectivity. So the connectivity means both solid connectivity and pore connectivity. For example, here this is the pore structure. So the colored pores, rather than the green pores, are disconnected, or they are all different components. So for this one, they indicate that these pores will be closed after we generating the porous structure. So we need a connected pore structure. So we want to guarantee this, and here we use we consider the connections of the pores, but which is the effective and efficient connection criteria to measure the connection of between the pores is a problem. So here we employ the Moss-Mel complex, which is really a good one for representing the topology connections. So still, we show it in a 2D case. So here, this is a 2D case, and it can be seen as a scalar field, and higher location means higher value. And for the whole space, we have 3 critical points. That is the local minimal, that is the green dots, and we also have the saddle points, that is the green blue dots, and we have the blue dots as the maximal. That is the local minimal, saddle points, and the local maximal points. So yeah, these are the 3 parts of the print of the critical points. So we can see that along this white color green lines, this white color gradient lines, and we can compute the the MSC cells which are connected by the critical points. For example, here this one we can see the a minimal connect to the saddle and then connect to the maximal point. So if we take a look into one cell, all gradient lines starting from the minimal point and will end up at the maximal point. So all cells have the 2 saddle points and 1 minimal and 1 maximal. So for the 3D case, it's a little bit complicated, but still we have minimal, maximal, but we have 2 different kinds of saddle that is called 1 saddle and 2 saddle. So these are the basic principle of the MSC function. So we can combine the Gaussian kernel with this MSC function. That is, we only need to build two MSC complex. That is, one is only containing the maximum and 2 saddle points, and the other only contains minimum and 1 saddle points. So let's see a specific example. So here we want to connect the pores, and then we need to consider which are the best connection option for the pores, and we follow the MSC cells consisting of the maximum and 2 saddle points. So we get this connected pores, and we also have the solid one. So if we consider to connect the solid part, which is not often used, we can still guarantee the solid part to be connected using the minimal and 1 saddle points as the complex element. So for the connection, we employ the fat curve, which is a trace by a moving sphere of changing radius like this one. Okay, so that's the basic technique. So we have we can get the results, and we can control the porosity here. For example, the upper row is the 80% porosity and with different tensor fields. And we can also control the pore size. And all our motivation is to compute the biomimetic porous structures, that is organic porous structures. I can also use this modeling as the kernel design for with some given tensor field. We can achieve some various shape pore shapes, and then we can get different results. Also, we consider how to model the real the bones as the porous structure. Here I mentioned that for the implant, it does not need to be not to be biomimetic. As we can see, there are many regular implants has already been used in mechanical applications. So here we consulted with doctors, did not need to be organic. So here it's just an example to show the modeling result. Still, for this kind of vertebra model, the porosity is usually 60%, and we have the pore size as the 0.5 millimeter, and we get this result. But we can also tune the objective function. We can optimize the area, the internal area, such that we get the higher heat exchanging efficiency. So we can see that all the optimization is working on the pores, that is on the Gaussian kernels. So that's really the basic idea. We can also do the strength optimization, but still I admit that our goal is not to generate the most efficient internal structure with the highest stress to weight ratio. We want to maintain the organic shape of the porous structures. So as shown here. So the middle one is a CT scanned bone structure, and so our model, I think, is more close to the real scanned one. Okay, so we have some fabricated results, and models are also online. Okay, so as a conclusion, I just introduced two of our recent works. One is the implicit function driven as the middle one, and the other is driven by the parametric kernels. But the kernels is used to representing the pores. All of the three methods are top-down approach. That is, we follow the we optimize structures in a global manner in the given shape. So here I want to add a little bit comments on these different kinds of approaches. For the top-down approach, I think it is coupled optimization of geometric structures and physical properties in a global data space. And it needs high computational cost. At least mostly needs high computational cost, at least as it is a coupled optimization. We need to consider the simulation, the finite element analysis, and the structure parameters. So I don't think it would be a good choice for a high resolution of the structures like microstructures. So microstructures as a bottom-up approach, its feature is decoupled optimization, and it's feasible for high-resolution structures, and it has high generalization capabilities as a new material, so-called metamaterial. Okay, so still, I think the trend is to combine the top-down approach and bottom-up approach as the two-scale one. This is also our current interest. That as shown here, we are really interested to make the structures to be very dense and to convey real different material properties. We use just one single material, and we can convey the very large variety of material properties. So that's our goal. Okay, so I think this concludes my talk, and I apologize again for the minutes wasted on my side, and thank you for your attention. Thank you.
Okay, thank you, Linda, for the nice presentation. It's really inspiring. So we have one question from Haisen for the two speakers. So, hi, Ligang. I'm not sure, Ligang. Hi, Ligang, can you hear me?
Yes, I'm around.
Okay. So, is it possible to on the video so we can see you? Okay. Yeah. Okay. So we have one question from Haisen. He asked about, is that possible to apply deep learning to stress analysis for such complex porous structure?
Okay, yeah, my answer is yes. And actually, there have been a couple of works which have applied machine learning or deep learning or data-driven methods to generate the lightweight structure or porous structures, as far as I know. So yeah, because we know that there are lots of optimization and the computational cost in the whole process, and if we can pre-compute some data, then we can definitely apply these technologies. So this is my point of view. But the challenge is how we can formulate the optimization into a data-driven or machine learning or deep learning framework or architecture. So people are trying very hard to solve these problems, as I know. So my answer is yes. So maybe Linda can have more comments.
Ditto, I have the same answer. And I think with the trend for more complex geometries, for example, the microstructures, the microstructure is really nice because it's regular. It's in a regular hex, for example. So I really think deep learning techniques would have a large chance to help to analyze the structure to physical properties relationship for very random generated microstructures, such that we can close the loop and we can really have the capability to generate microstructures and with target physical properties. So yeah, that's my answer.
Okay.
So hold on a second. So I have another comment that during the last few years, so we have known that there are lots of architectures called differentiable rendering or differentiable simulation. So we can replace some non-differentiable process by some differentiable computation process into the whole optimization. So that's a very high possibility that we can apply differential simulation to the whole the problem. So this might be a very exciting or promising direction. And actually, some of my students are still already working on this direction. So this is another aspects how deep learning can be applied on our problem.
Okay, so both speakers agree that this will be a promising direction in computational fabrication. Okay, there is one more question from the audience. So from Zheng Manun. So she says, hi, Professor Liu. I'm new to this area. I work on physical simulation. So recently I'm interested in modeling daily objects made from foams. So can you please share your opinions on how can we build a good model for foams? There are also porous structure.
Yeah. Okay, so actually, yeah, fabrication can be considered as a physical simulation. So many years ago, when we didn't have such kind of simple fabrication machine like 3D printers, we can do virtual simulations, and we have lots of simulation works. And then now on, we can materialize the results produced by the simulation. So there are lots of possibilities to apply simulation into real fabrication. But there are more and more issues during the fabrication. So we can couple the simulation and the fabrication together into more challenging problems. So let me answer the question that how can we do the porous or the lightweight structured representation, optimization, and analysis. So this is a challenge that in my talk, in the last session of my talk, and the problem is that during the scale of the problem is becomes larger and larger. We need more and more efficient technology to solve such kind of large scale problem. So this is a challenge for us. And I think that we do have some probabilities on this direction, and we can discuss offline if you have any other comments. And one of my students is working on how to reduce the scale of the simulation into in the finite element methods, and that is we can divide it, the large scale problem into a set of small scale problems, and then put them together into a larger one. And the difficulty is that how can we combine the small set of scale problems into the larger one, and we are still working on that. And another direction is how can we apply the GPU or parallel computing technology in this large scale simulation stuff. Okay.
Okay, so do you have any comments about this question? So she asked about how to use it.
Form, right?
Foam, yes, FOAM, foam, yes. Yep.
What?
FOAM.
Foam. Okay. Foam is very typical Porous structure.
Yes.
And I think foam has very forms as of course, you can use our Gaussian kernels to build these forms, and forms I think is most very regular, very isotropic distributions of these pores. So actually, there are a number of researches on producing the forms. We can also use the geometric texture synthesis methods to synthesize the forms. We can also apply the stochastic manner to mimic the real production of this kind of form structure. Because as we know that the form structure has been well developed industry, especially the uniform distributed form structure, and they have very efficient way. For example, they put some material inside the whole space, and they can let the air escape, and they just form the pores. So my idea is there are really many options to model these forms, and if you need to consider the constraints and objectives of your form structure, like whether it's uniform, whether it's like blue noise sampling, it's the distributions, and you will have the choice.
Okay.
Hi, Lina. So as I have know, the industry, the material science industry, do many experiments. I mean, the physical experiments to produce form structures in their community. So the computational model is very complicated from my point of view. So I think that the representation of the form is very challenging. So do you think the volumetric representation is the only one, or is there any other options?
I think I don't think the volumetric optimization is would be the final choice. I think I think mostly it need to be some parametric one. Otherwise, we cannot afford such huge computational cost. And right, it would be if we I would recommend the bottom up approach. Yeah, the bottom up approach. So for example, we have different tiling methods in computer graphics. Like we can maintain the connectivity between the tiles, and also we will keep the non-repetitive artifact. We can like one tiles. One tiles has the can produce the connected tile, and also with the irregular distributions of the tiles. It would be an option to, I think.
Okay. So that means that do you prefer to apply the synthesis-based methods to produce form structure, and or data-driven? That might be another good option. The synthesis-based methods or learning-based.
Actually, my view is to combine learning-based method with the bottom-up approach. I think that would be the trend. Yeah, to employ the learning method to generate this 3D the microstructure with target properties, and then do the bottom-up approach. Yeah. So I think the combination occurs in this level. That's my aspect.
Okay. Thanks.
Okay. I think due to the limited time, I think we will not be able to respond all the questions from the audience. So if the audience have more questions, we can move to the Discord, and we can there we can do informal discussion. Okay, so that's the end of this seminar. So thank you again for the speakers. Nice talks.
Okay, thank you.
Okay,
Thank
see you in the
you.
Discord.
Thank you. Bye.
Bye.